just as we've brought in the notion of center to the world of random variables and probability distributions, we can also bring in a notion of a measure of spread or variation. To illustrate this, I have an example here of a probability distribution graph corresponding to observing a roll of a D20 die, which is popular in certain tabletop games. The idea being that it's a 20-sided die, and if it's balanced, each side, 20 of them, is equally likely to appear every time you roll. So if we think of the random variable represented here, this has the discrete uniform distribution with parameter n equals 20. Okay, the squiggly line that I drew here can be read as is distributed as. In other words, has the distribution that we're describing right now. So, standard deviation, we defined it previously when we were talking about samples. Specifically, we had, for standard deviation of a sample, or actually I actually wrote that's for a population, so I'm going to be consistent and write population, is the mean deviation of data values from the population mean. And when we're doing this, we always have to take the mean first and then calculate sigma. So then we calculated this as the square root of the sum over all data values of the data values themselves minus the mean squared all over the number of data values. And similarly to what we did with population mean and how we wrote it slightly differently, because some of these data values might be the same, they might coincide, especially if we're talking about discrete data, it might be appropriate to write this instead as the sum of these specific or unique deviations or square deviations. I messed that up here. Square deviations times the relative proportion, so the proportion of this deviation over the population size n, all under the square root. And it's in that spirit that we now define, so new definition, we're not rewriting it, but for random variables, this is going to be slightly different. The standard deviation of a discrete random variable will be written as sigma is equal to the square root of the sum over all possible outcomes for this random variable of the outcomes minus the expected value squared times the probability of that outcome. So to remind you, this is expected value. This is the outcome And we write one of these terms for each unique outcome, not for each one that we observe in a specific simulation. And P of X is the probability mass function applied to that specific outcome. And you might guess, so if this is standard deviation, you might be wondering, is there a variance too? There is. Variance, which has the same notation, sigma squared, is just this exact same calculation, or computation, but without the square root. So both are a measure of spread for the outcomes of a distribution, and we use them in different for slightly different needs. So for instance, standard deviation is very helpful for determining how far away a specific outcome is from the mean. So it helps set us some boundaries on what we consider normal or not significant versus significant, and we'll talk about that later. But first, let's actually practice. So, question. Recall that we were working with X having the discrete uniform distribution with n equals at 20. So what is the standard deviation for X? Well, we would need first the mean. So we'll have to calculate that first. So step 1, find the mean or the expected value. So we're going to sum over all the outcomes and find all these products, the outcomes times their probabilities, which is going to be 1 times the probability of rolling 1 plus 2 times the probability of rolling 2 plus, and so on, all the way until we get to the very last one. The fortunate thing here is that all the probabilities are the same, and so this calculation should be 1 times 0.05 plus 2 times 0.05, and so on. And we end up with 10.5 being the expected value. Now we can calculate the standard deviation. So remember, that's going to be the square root of the sum over the outcomes of now the square deviations. So the outcome minus the expected value squared times that probability. So each term will look like 1 minus 10.5 squared times 0.05 plus 2 minus 10.5 squared times 0.05 plus, and so on, until we get down to the very last one. And we take the square root of all of that. Make sure you do that at the very end. Do not do it individually, because that won't be the same answer. And if you take a minute so pause the video if you want and do this calculation on your own. But I do have the answer in front of me. I've done this calculation already. And I find that the standard deviation is 33.25.